Alright, let's talk about some of the properties of logs today. So we're going to look at the change of base formula, converting from an exponential to a log and a log to an exponential, which is the most important thing you need to know in logs. And then we'll look at how to expand and condense logs as well. So first things first. If we have an exponential equation, let's say a to the x equals y, and remember what makes it an exponential equation is that the exponent is a variable. So this gets converted to a log, or we can change it to a log, I should say, and this will become log base a of y equals x. So this is how we can go back and forth from a log equation to an exponential equation. Notice that the base of the log, a, is the same as the base of the exponential. And then what we're taking the log of, so y, is what the exponential equation equaled, and the exponent in the exponential equation, x, is what the log equation equals. That right there, that conversion between exponential and log, is the most important thing you need to know about logs, and it helps you solve log and exponential equations. Okay, now let's look at the change of base formula. So the change of base formula allows us to take a log of any base and convert it to any other base that we want. This is really only useful if we want to change something into log base 10 or log base e, which is natural log, so that we can type it into our calculator. But the general equation is if we have some log base a of b, I can change this into log base c of b over log base c of a. Now again, c can be any real number we want. It has to be greater than 0 though. But this is really useful because then this is also log base 10 of b over log base 10 of a. Log base 10 is our common log, or the log button on the calculator, and this is also natural log of b over natural log of a. And natural log again is a button on our calculator. Natural log is log base e. Okay, now let's look at expanding logs. So this is a property of logs. It directly relates to our properties of exponents. And what it does is it allows us to take a single log expression and spread it out or split it up into multiple log expressions using addition or subtraction, depending on what we were originally given. So for example, if we have some log base a of x times y, since this is multiplication with what we're taking the log of, this expands using addition, and so it becomes log base a of x plus log base a of y. The same thing is true if we have division within what we're taking the log of. So if I have log base a of x over y, notice that I'm not dividing two separate logs like in the change of base equation. This is a single log where what I'm taking the log of is a ratio or division. This expands into log base a of x minus log base a of y. So now when we had division within the log, we separate it into two separate logs of subtraction. When we had multiplication, we separate it into two separate logs with addition. Notice that the base of the logs all stayed the same here, in this case base a, where a is some positive real number. So if we combine these, and let's say we have log base a of x, y over z, this becomes log base a of x plus log base a of y minus log base a of z. The opposite is then true as well. If I start with some log base a of x plus log base a of y plus log base a of z, now I have three separate logs. The key thing is they all have to have the same base, and they're being added together, so I can combine them into a single log with that base and make this log base a of x, y, z, where the x, y, and z are all being multiplied together. And the same is true if we have a subtraction in there somewhere. So if we have log base a of x minus log base a of y plus log base a of z, now we'll combine these just in the order in which they are written. If there are parentheses somewhere, then obviously we do what's in the parentheses first. But in this case, since it's one single expression written out, we just go in the order in which it's written. So we'll combine this into log base a of x over y plus log base a of z. And then our final step, now I have just addition of two separate log expressions, and so this becomes log base a of x times z over y. The last property of logs that we'll talk about, going along with the expanding and condensing of logs, is what if there's an exponent. So for example, if I have log base a of x to the n. Now notice that the exponent n is, we're considering this any real number, and also it is an exponent on the x only. This is not the same thing as log base a of x to the n. These are two different expressions. They do not equal each other, and this one here on the right does not follow the property that I'm going to show you. So we're going to ignore that for now. So again, if I have log base a of x to the n, now the property is I can bring that exponent down in front. So this becomes n times log base a of x. So now we can combine that with the addition and subtraction properties as well. For example, if I have something like log base a of the square root of x times y over z. So now this will expand into 1/2 log base a of x plus 1/2 log base a of y minus log base a of z. So the 1/2 in front comes from the square root, which is an exponent of 1/2. Notice that the square root was only on the x and the y, so therefore it is only in front of the log base a of x term and log base a of y term, and it is not in front of the log base a of z term. Had the square root been around the entire quotient of x, y over z, then there would be a 1/2 in front of the log base a of z as well. Also notice that if we had been given this, as our expression initially, and we wanted to condense this into a single log, then we would follow the exact opposite of what we did to expand it. So we could bring the 1/2 up as an exponent, the 1/2 up as an exponent, understand that that's a square root, combine the x and the y using multiplication, and then divide by the z. Okay, the last thing we're going to talk about briefly are graphs of logs. So if we understand that an exponential equation and a log equation are inverses of each other, let's look at the relationship between them again. So that, remember, this is the most important thing between exponentials and logs, is understanding that if I have some equation y equals a to the x, I know this converts to log base a of y equals x. Now, a couple things I want to pay attention to first in the exponential equation. Well, in order for this to be an exponential equation, a has to be greater than 0 but not equal to 1. Hopefully I can understand that if a was negative, this function would not be continuous, and if a is 1, then 1 raised to any number is still just 1, so that's just going to be a horse on a line. So that's why a has to have those properties. So then that also must hold true over here. A has to have those same properties. Now also pay attention to, well, if a meets these requirements, that it's greater than 0 but does not equal 1, then what does that tell us about y? Well, that also tells us that y is never going to be, or I'm sorry, y has to be greater than 0 as well. But y can equal 1 in this case. When would it equal 1? Well, it would equal 1 when x is 0, because anything to the 0 power is 1. Okay, so now let's look at the graph of a log, having a little bit of understanding about that. So let's look at the function f of x equals the natural log of x. Okay, so what is this graph going to look like? Well, let's talk about some things that I know. I know that x is not going to be negative ever, and it's not going to equal 0. That tells me, or I know that because of what we talked about up here, in that for this equation I have y in that location, but remember this is just a variable here as y. It is not representing necessarily y on my xy plane. So this variable y has to be greater than 0. In this way I've written the function, that is x. So I know x has to be greater than or equal to 0. Therefore I know I have a vertical asymptote when x equals 0. What else do I know? Well, I know a key point that every log equation, so if I look at this equation here, has to go through the point 1, 0. Well, how do I know that? Well, that's telling me that if this value right here is 1, that's saying a to what value equals 1? Well, anything to the 0 equals 1. So my graph, if I draw a general sketch, I know I'm going to have a vertical asymptote at 0, and I know that the graph is going to go through, so obviously this isn't perfect, but it's going to go through the point 0, 1. The actual graph is going to look something like this. Now I also know one other point, and it's not going to be a nice point here, but I know that this graph is going to go through the point e comma 1. Now how do I know that? Well, I know that because natural log has a base of e, so if I look up here, that's saying e to the what equals e. Well, e to the first equals e. And so if we go to our calculator, we know that e is 2.78 approximately. So around here I'm going to be, this is going to be, and again this isn't perfect obviously my graph, this is the point E1. So that's how I can graph a log function. They're all going to look the same as this unless we shift or reflect them in any way following our properties of functions.